So this is an example of how to use Gaussian elimination to transform a system of linear equation into augmented matrix, and then you use the augmented matrix to transform it into its row echelon form. Okay, so as you can see that this augmented matrix here contains 5 rows and 6 columns, right? That means you have, and you look at this matrix here, the coefficient matrix, you have 5 rows and 5 columns. That means this is the system of linear equation that has 5 variables and 5 equations. And this is the last column is the constant column or the constant matrix. So now we want to transform this augmented matrix into its row echelon form, okay? We always want to look at the first row, see if it's in a good shape. So look at the first row. The very first entry is non-zero and it is 1, so it's in the good shape, right? It's satisfying the first condition. So we just keep it like that. And then we look at the second rows, right? Third row and so on. And we know that the number of zeros, right, in the second row, the number of leading 0 entries of the second row has to be more than 0, so it has to be at least 1. So maybe we think about, okay, I can 0 this out, right, to make it 0. So then the number of leading 0 entries of the second row is more than 0. But then I can see that I look at my fourth row here, it is already 2 number of 0. So somehow I think I can just move this row to the second row. I use the first row operation, so I just interchange the fourth row with the second row. Okay, so this is maybe my first operation that I want to do. So 1, and the first row is staying the same. The second row will be 0, 0, 1, 1, 3, 3. And the third row should -2, -2, 0, 0, 3, 1. The second row is -1, -1, 0, 0, 1, -1. And the fourth row is the same, 1, 1, 2, 2, 4, 4. All right. So now I look at my second row. It's good, right? Because the first non-zero entry is 1. The number of zeros is more than the number of zeros up here, so I'm good for now. How about this one? So that means if I go to the last row, the next row, the third row, the number of leading 0 entries has to be at least 3. And at this point, I don't have a 3. I don't even have a 1 leading 0 entry, so I have 2. So my next strategy is I have to 0 this out, 0 is out, and somehow 0 is out as well, right? It's already 0. So what is my strategy here? So I have to use the first row here in order to 0 this out. So first, make -2 equals to 0 using the first row. So my next operation will be row 2 is row 2, right, plus 2 row 1. All right, because -2 plus 2 times 1 is -2 plus 2 is 0. How about the fourth row? I can do simultaneously. I can use simultaneous row operations as long as I use each row separately. So now I go to row 3. I also use row 1, right? Because row 1 is the one that is fixed, is the one that is good to go. So row 3 plus row 1, because -1 plus 1 is just 0. And the last one, row 4, I would have row 4 minus row 1. 1 minus 1 is also 0. Okay. Now I have 3 row operation. I apply these 3 row operations on my matrix here at the same time. So I have 1, 1, 1, 1, 1, 1. And the second row still stay the same. This row will be -2 plus 2, right, is 0. -2 plus 2 is also 0. 0 plus 2 is 2. 0 plus 2 is 2. 3 plus 2 times 1 is 5. And 1 plus 2, which is 3. All right. About the fourth one, -1 plus 1 is 0. -1 plus 1 is 0. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 2. -1 plus 1 is 0. How about the last one? 1 minus 1 is 0. 1 minus 1 is 0. 2 minus 1 is 1. 2 minus 1 is 1. 4 minus 1 is 3. 4 minus 1 is 3. Alrighty. Now I have a new matrix, right? And then now, so the first row is checked. And and I can see that the second row and the last row are the same. So if they are the same, what I can do is I can take one, subtract the other. So then one of the rows will be become a 0 row, right? So that's one operation that I can do. I can take row 3, row 5, and I take row 5 minus row 2. Okay. What else I can do? Well, let's do that. So if I do that, then the last row here will be 1 minus 1 is 0, 1 minus 1 is 0, and so on and so forth. That's going to be 0, right? At this point, I know that so in the previous step, my first row was good to go. And then as you pay attention to all of these operations, I replaced row 2, row 3, row 4 by applying operations to the first row, because the first row, row 1, is the good row, right? Is the row that is in the good shape. So that's why I use the first row to operate the row 2, row 3, and row 4, and so on and so forth. Oh, this should be row. I did row 3, 4, 5, not 2, 3, 4. 3, 3, 4, 4, 5, 5. Okay. All right. And then when I use a row to change all the rows, that is, and I can give this row 1 a name, and it's called a pivot row. So at this point right here, row 1 is a pivot row. So row 1 is a pivot row. And you know that it is a pivot row because it's the row that is in a good shape, that satisfies all the conditions so far, right, to be in the row echelon form. And I use the first row, row 1, to transform all the rows, so then I can achieve my goal, which is transforming this augmented matrix into a row echelon form. So row 1, it was a pivot row, right, in this step. Now the next step is I move my pivot row to row 2, because row 2 again is in the good shape. Row 2 is in the good shape, right? So the number of leading 0 is more than is 2, more than 0. And then the first non-zero leading non-zero is 1. So then I'm good to go, right? So now I move this second row to the pivot row. At this step, the second row is the pivot row. And I can use the second row to transform all the rows. So first step is I take row 5 minus row 2. And the second step is what I'm going to do is I want to, again, if you look at row 3, you need to have at least 3 leading 0 entries. So that means you need to zero this out. How can I zero this out? I need to use row 2 to get rid of the 2 here. So row 3, right? I want to transform row 3 in such a way that I take row 3 minus 2 row 2, because 2 minus 2 times 1 is 2 minus 2 is 0. Okay. So that's helped me to make this equal to 0. And how about the row 4? You have to do the same thing when you use row 2 to zero out this entry. So I need to transform row 4 in such a way that I would take row 4 minus row 2, because 1 minus 1 is 0. Okay. Well, so now again, I have I apply 3 row operations, transforming row 3, 4, 5 using row 2, because at this point, row 2 is a pivot row. Let's write out the new matrix. So the first row stay the same, 1, 2, 3, 4, 5, 1. The second row stay the same because it's now a pivot row. Okay. Let's see, the third row would take row 3 minus 2 row 1. So it's 0, 0, right? 0 minus 0, 0, 0. 2 minus 2 is 0. 2 minus 2 is also 0. 5 minus 2 times 3 is 5 minus 6 is negative 1. And then 3 minus 2 times 3, 3 minus 6 is going to be negative 3. Okay. How about row 4? Row 4 minus row 2. So 1 minus 0 is all 0, right? 1 minus 1 is 0. 1 minus 1 is also 0. 2 minus 3 is negative 1. 0 minus 3 is negative 3. Okay. And then the last operation is R5 minus R2, so 0, 0. And we know that because R2 and R5 are identical, that means the result for this operation will be R0. All right. Now, at this point, we want to check how many rows are in the good shape. So the first row is good, right? The second row is good. The third row is not good because it has to be, so this non-zero entries here has to be 1, and we can do that by multiply the third row by negative 1. Okay, and then we can see that the third row and the fourth row, they are the same, so we can apply another similar to this operation in order to get rid of one of the row. Okay, so the next operation will be R3 is transformed using R3 times by negative 1, right? Just negative 1 multiplies to negative 1. And then also R4. Oh, we can do R4 later. So using 1 operations, transforming the third row into 0, 0, 0, 0, 1, 3. And then the fourth row will stay the same. And then the last row, of course, is still a 0 row. Okay. And keep going. So the first row is good. The second row is good. The third row now is good. So now the third row is a pivot row. Okay. The third row is pivot row, then you need to make sure that the fourth row has more number of leading 0 entries. So that means this, you have to make this entry here be 0. By using a simple row operation, I will replace row 4 by row 4, right, plus row 3, because -1 plus 1 is 0. Okay, let's see. Then again, I still have my first row. I still have my second row, which is already in a good shape. The third row is a pivot row right now. That means it's already in a good shape. The fourth row now is been transforming to -1 plus 1 is 0, -3 plus 3 is also 0, and the last row is still a 0 row. All right. So now if you look at this matrix here, you have 2 0 rows. They are in the bottom, which is good. All of the non-zero entry of non-zero row are 1, which is good, right? And then the number of leading 0 entries of the second row is more than the number of leading 0 in the first row, and also the number of leading 0 entries of the third row is more than the number of leading 0 of the second row, which means this matrix here is in the row echelon form. Okay. So now, since the matrix in the row echelon form, and again, our goal is to solve for this linear system, right? Well, once you transform it in the row echelon form, you can solve for it. And if you use this matrix here, how can you solve for x1, x2, x3, x4, and x5? So the first one is x1, x2, x3, x4, and x5, okay? Then I can say that x5, so again, x1, x2, x3, x4, and x5. If I look at the third row here, I can translate this matrix back into a system of linear equations. So if I translate it into a system of linear equation, I will have x1 plus x2 plus x3 plus x4 plus x5 equals to 1. And on the second row, I have x3 plus x4 plus 3x5 equals to 3. And the third row, I have x5 equals to 3. So this is a system that I translated from this augmented matrix. Okay, and from this system, I know that x5 equals to 3. Okay, and I know that so that's the only information that I know from here, right? And then I have to solve for x4 using x3 and x5, x1, and so on. I have to solve for x1, x2, x3, x1, x5. How can I solve for it? So again, we look at this equation, the system here is a system of equation. Now we only have 3 equations, but we have 5 variables. 5 variables, right? But 3 equations. Okay. That means we will have more than 1 solutions. Another terms is you will have many, many solutions for the system. How can we solve for the solutions? So as you see, back to this matrix here in the row echelon form, you have 3 non-zero leading coefficients, right? 1, 1, 1. By the definitions, because these 3 equations here are, these 3 rows here are the pivot rows. That means this non-zero, this leading non-zero coefficients of all the pivot rows are in the pivot position. And since this pivot positions here is in the first column, So the first row, the first column here is the pivot column, right? So you have pivot row, and then you also have pivot position or pivot column. And you can see, and you can say that this variable, so this pivot positions corresponding to what they call the leading variable. For example, x1 will be your leading variable, x3 will be your leading variable, and x5 will be your leading variable. So x1 is leading variable, x3 is your leading variable, and x5 is your leading variable. So by the definition, leading variables are the variables that correspond to the first non-zero element in each row of the reduced matrix. So one here is in the pivot row, the first non-zero entry of the pivot row corresponding to x1. That means x1 is a leading variable. So according to this matrix, I have x1, x3, and x5 are the lead variables. So the rest of the variable x4 and x2, so x2 and x4, right? Let's say x2 and x4 are free variable. So since x2 and x4 are free variable, then that means you can have an arbitrary value for free variable because they are free. So that means you can let x2 equals to alpha, and alpha is a real number, and x4 equals to something else, right? Different variable. Let's say beta, and beta is a real value. So you assign a value for x2, you assign a value for x4, then you can solve x1, x3, and x5 according to the values of x2 and x4. So the solutions for this system here will be, in this one, I know x5 equals to 3. I know I set x2 equals to alpha. I set x4 equals to beta. How can I solve for x3? x3 equals to 3 minus from the second equations, right? x3 equals to 3 minus 3x5 minus x4. And from what I know from x5 and x4, I can solve for x3, which is equal to 3 minus 3 times 3 minus x4, which is beta. So you have 3 minus 6 is negative 6 minus beta is your x3. How about x1? So x1 equals to 1 minus x5 minus x4 minus x3 minus x2, which equals to 1 minus x5 is 3 minus x4 is beta, x3 is 6, negative 6 minus beta minus x2 is alpha, which is 1 minus 2, 3 is negative 2 plus 6 is 4, and then you have negative beta and minus plus beta is a 0. So then you just have negative alpha x1. All right. So now you have x1, x2, x3, and x4. The solutions of a system of linear equation will be a tuple, right? A fine tuple. x1 first is 4 minus alpha. x2 is alpha. x3 is negative 6 minus beta. x4 is beta. And x5 is 3, where alpha and beta are real numbers. So as you can see that this is the solutions of the system. And based on these solutions, you know that this system has infinitely many solutions because you have infinite many different values for alpha and beta. Thus, the number of solutions for this system is going to be infinitely many. And this is how you describe your solutions. If you assign a value for alpha and beta, you can figure x1, right? x3 and x5 is already fixed. So for any value of alpha and beta, you will have a solution corresponding to those values. And you have infinitely many value for alpha and beta. So this is an example of how you first transform, right, using an augmented matrix of a system, transform using row operations, transform it into the row echelon form, and from the row echelon form, you can use a back substitution to solve for the variable x1, x2, x3, and x5 using pivot positions, right, which are leading variables. Identify leading variable using your row echelon form, and leading variables that are the variable that corresponds to the non-leading zero of each pivot row. Okay, and then once you have leading variable, then you can identify free variables. So free variables here will help you determine. Once you determine the free variable, you should assign your free variables to an arbitrary value. Usually I just use alpha, beta, gamma, or A, B, C, D, but you know that those letters representing for just an arbitrary number, arbitrary real numbers, right? You assign those, and then you can use those variables, right, to solve for the rest of the variable, to solve for the leading variables. And once you have definitions or relations or the form of leading variables and the free variables, you can put everything into an n tuple as the solutions for the system. Since the system has 5 variables, that means in your solutions, right, you have an n tuple, like 5 tuple as the solution of the system. And then you want to identify, we want to point out that alpha and beta here are arbitrary values that are arbitrary real values that you can use.